Good morning everyone. Today we will be continuing with the chapter of aldehyde, ketone and carboxylic acid. We have completed aldehyde and ketones method of preparation and chemical reactions. We will be starting with carboxylic acids. Carboxylic acids are those organic compounds which have COOH functional group present within them, which is known as carboxyl group. It is a combination of two words, carbonyl and hydroxyl, therefore carboxyl. Their classification depends on the number of carboxylic acid. They can be classified as monocarboxylic acid containing one carboxyl group and dicarboxylic acid containing two different carboxylic acid groups. The common names of carboxylic acids are given here. Ethanoic acid, which is known as formic acid, which is found in the sting of the red ant, Formica. Ethanoic acid, acetic acid, which is known as vinegar, and butyric acid, which is known as butanoic acid, is a form of butter. The nomenclature is done by replacing the E of alkanes with oic acid at the end of it. Therefore, they are also known as alkanoic acid, such as we have discussed before, methanoic, ethanoic, propanoic, etc. Now we have, if the group is attached on a benzoic ring, then it is known as benzoic acid or benzene carboxylic acid. Benzoic acid is the common name which we generally use in our chemical reaction. This is 2-phenyl acid. Since carboxylic acid has higher priority than the phenyl ring, therefore the numbering and nomenclature is based on it. And this is benzene 1,2-dicarboxylic acid, also known as phthalic acid, which we will use further in the amines chapter when we will do Gabriel phthalimide synthesis, and further in this chapter also. Now they can be prepared by primary alcohols and aldehydes in the presence of strong oxidizing agents such as KMnO4. This is Jones reagent, CrO3.H2SO4, and Tollens reagent also. They can be prepared from alkyl benzenes such as toluene when we do strong oxidation of them such as KMnO4 KOH, and then hydrolysis leads to the formation of benzoic acids. Whatever the number of carbon chain is, it simply gets converted into benzoic acid and the rest of the molecules are removed as carbon dioxide and water. Now the next method is from acid derivatives such as amides, halides, esters and hydrides, etc. On hydrolysis with carboxylic acid, they can be converted into carboxylic. They can also be prepared from nitriles and amides by hydrolysis. Cyanides can be hydrolyzed to form amides, and those amides on further hydrolysis yields you carboxylic group such as aliphatic and aromatic amides, both give you carboxylic acid derivatives. From Grignard reagent also it can be prepared when Grignard reagent reacts with carbon dioxide in the presence of dry ether. We get this compound which can be further hydrolyzed to form carboxylic acid. Now some physical properties of carboxylic acid. Aliphatic carboxylic acids up to 9 carbon atoms are colorless and liquid at room temperature with unpleasant odor. The higher acids are wax-like solids. Lower carboxylic acid are miscible in water due to intermolecular hydrogen bonding. However, solubility in water decreases due to increase in size of alkyl group. Monocarboxylic acid have higher boiling point as compared to alcohols of comparable molecular mass due to presence of stronger intermolecular forces, as you can see here. Melting point of monoaliphatic carboxylic acid show alternation or oscillating effect. The melting point of an acid with even number of carbon is higher than the next group. This is due to the zigzag pattern chain of CH3 and COH groups. Glacial acetic acid is completely pure acetic acid present in solid state below 16.6 degrees Celsius. Now chemical properties of carboxylic acid. Carboxylic acid do not give reaction of carbonyl group as it enters into resonance with lone pair of oxygen of hydroxide group. Here are some important reactions shown by carboxylic acid. First is the bond cleavage of OH bond, which we have done in alcohol phenol ether also. It can also show similar reactions. With sodium, it forms sodium salt and release hydrogen gas. With zinc, it forms zinc salt, release hydrogen gas. With NaOH, it forms again sodium salt, release water. With sodium bicarbonate, it releases carbon dioxide gas, which is also a distinguishing test for this species. And with sodium carbonate also, it releases carbon dioxide gas. Above, the last two reactions and others also can be used to detect the presence of carbonyl group in an organic compound. Now, carboxylic acid dissociate in water to get a resonance stabilized carboxylate ion and hydronium ion, and this structure is extremely stable, which is the major reason for the extreme acidity of the carboxylic acid. The acidity of any species is measured by the dissociation constant, which is known as Ka, also known as acidity constant. A stronger acid will have a higher Ka but a less pKa, which we have discussed before also. pKa is inverse of minus log Ka, and the similar logic goes for basicity when we would be studying about amines. Now, when electron releasing substituent plus I effect are attached on the carboxylic acid chain, it decreases the acidity of the carboxylic acid by destabilizing the carboxylate ion. The order of plus I effect goes in this order. Therefore, the order of acidic strength, the highest strength belongs to methanoic acid, then ethanoic, then propanoic, and then butanoic acids. On the contrary, opposite of plus I effect, the substituent groups showing minus I effect such as halogens and nitro groups increase the acidic strength by decreasing the magnitude of negative charge on the carboxylate anion and thus stabilizing it. The release of H plus ions becomes relatively easy. As you can see here, the number of halogen atoms we add, it increases the acidity of the carboxylic group significantly. The more closer the halogen group is to the species, the higher the acidic strength would be. The order of negative I effect goes in the following order: fluorine, chlorine, bromine, and then iodine. Fluorine having the highest effect on acidity. The acidic strength of aromatic acid. The parent member of the family benzoic acid is a relatively weaker acid as compared to formic acid but stronger than acetic acid. So you would have to remember this order. Acidic strength of carboxylic acids. In the presence of minus I effect group, the orthoisomer has more than the meta and meta has more than the para one. Similarly, in methyl substituted cases, it follows a similar order due to ortho effect. We will continue with the reaction of involving cleavage of COH bond. These reactions would be a little similar to the ones we have done in alcohol phenol in ethers also. First is the formation of anhydride, which occurs in the presence of acidic medium or acids such as P2O5. This leads to formation of anhydride, and two different carboxylic acid groups are present here, and the water molecules between them are released in such a manner. Next, esterification. Acid in the presence of alcohol goes in a reversible method to form esters and water. The reaction mechanism is not a part of your course. The reaction with PCl5, PCl3 and SOCl2 are the same which we have discussed before in the alcohol chapter. So there is not much change here. Reaction with ammonia gives you ammonium acetate, and removal of water gives you amides. The same case goes for aromatic benzoic acids also. It forms ammonium benzoate. After removal of water, it forms benzamide. Now this is a major prominent reaction when we have dicarboxylic acid in the presence of ammonia, it forms ammonium phthalate. After removal of two molecules of water, one molecule of H2O from here and another molecule of H2O from here, the species left is CONH2, phthalimide, and after the removal of ammonia using strong heating, you form thalamide. This is a major product and it will be used in the amine chapter also for Gabriel phthalimide synthesis. Now reactions involving COH group reduction, it can be reduced by lithium aluminum hydride in presence of ether or B2H6 in the presence of acidic medium to form primary alcohol. Decarboxylation reaction using soda lime, which we have done in grade 11th also. Sodium salts can be reacted with NaOH and calcium oxide in 3:1 ratio to form alkanes. Electrolytic decarboxylation, which is known as coal-based electrolysis, yields you two different reactions on cathode and anode respectively. Huntsdicker is not part of your course. Still, for your knowledge, it forms silver salt of carboxylic acid, and on further treatment it gets converted into alkyl halide. Substitution reaction in the hydrocarbon part. This is your Hell-Wohlhard-Zielinski reaction, also known as HVZ reaction. When carboxylic acid are treated with X2 in the presence of red phosphorus, X2 can be any halogen, F2Cl2I2Br2. The halogen gets attached to the alpha hydrogen of the nearby carbon of the carboxylic acid group. In this case, this particular one hydrogen is substituted by halogen group. This is known as Hell-Wohlhard-Zielinski reaction. Now electrophilic substitution reaction of aromatic acid. Now carboxylic acid shows a negative resonance effect, therefore it is deactivating and always behaves as a meta-directing species, and it does not undergo Friedel-Crafts reactions because carboxylic acid is deactivating, and the catalyst such as a Lewis acid in the presence of AlCl3, it gets bonded to the carboxylic group only and it cannot act for its purpose of formation of an electrophile. This is a reasoning based question and can come in your examination, so kindly highlight the reason and remember, why can't carboxylic acids undergo Friedel-Crafts reactions? Now these are the reactions. Bromination in the presence of Br2 and Lewis acid FeBr3 gives you bromobenzoic acid. All the products will be meta-directing. HNO3H2SO4 gives you nitration, and only concentrated H2SO4 gives you sulfobenzoic acid. Formic acid is used in textile industry. Acetic acid is in manufacturing of rayon in plastic. It is also used in cooking in the form of vinegar 8 to 10%. Benzoic acid and its salts are urinary antiseptic, and formic acid can be used as reducing agent also. Now we have certain derivatives which come from carboxylic acid. When the OH group is replaced by certain groups such as Cl, NH2, OR or OCOR, which are respectively known as acid chlorides, acid amides, esters and acid anhydrides. To form acid chlorides, we just replace the OH group by Cl2 using PCl5 or SOCl2, which gives you acid chlorides. Combining two carboxylic acids as we have shown above gives you anhydride. When you react acid chloride with ammonia, you get acid amides, and carboxylic acid reaction with alcohol give you esters. They have different properties such as RCOCl gives you H2 palladium barium sulfate. Rosenmund reaction forms aldehyde. In the presence of benzene and AlCl3, it forms ester. In the presence of KCN, it forms COCN, which can be further hydrolyzed into a alkanoic acid, oxoalkanoic acid, which contains both a keto group and a carboxylic group. Acid amides show same physical reactions as you can show here. The major one here is Hofmann bromide degradation. This simply removes the CO group from the reaction and gives you primary amines as a byproduct. Lithium aluminum hydride also forms a reduction basis. These are the final few reactions from esters. In the presence of NaOH, salts are formed, saponification reactions. In the presence of ammonia, amides are formed. In the presence of reducing agent like lithium aluminum hydride, primary alcohols are formed. Anhydrides, reaction with alcohols form esters. Reaction of benzene ring and Lewis acid presence form aromatic esters, form aromatic ketones, and the reaction with uh, primary amines yields you this particular compound. This finishes your aldehyde, ketone and carboxylic acid chapter. Hope you understood it well. Thank you very much. Meet you with the next chapter of amines.